This is a quick and dirty little video giving some basic ideas about coordinate axes, vectors, and the stress matrix. If you're interested in a more in-depth and complete discussion of these topics, I would suggest that you look at Dave Pollard and Steve Martell's new textbook called Structural Geology, a Quantitative Introduction. We're going to be considering the stresses that are affecting a small volume, small cubic volume. The center of this cube is the origin of a coordinate system, and we're going to label that coordinate system in sort of a conventional way to begin with. We're going to change the labeling as we move along and become a bit more sophisticated. The z-axis is perpendicular to one of the faces of the cube, and we're going to call that face the z-plane. Similarly, the x-axis is perpendicular to another place. We call that the x-plane. And so this is going to be our way of labeling various planes by the axis that is perpendicular to them. So now we're going to take a look at the z-plane in particular and try and work out the stresses that are acting upon that plane. Our thoughts today are going to be centered around a small volume of mass that is in a differential stress field, and how do we go about defining the stresses acting on any particular plane within that stress field. Most of the time, and the exception is when we're dealing with principal planes, but most of the time the total stress acting on this arbitrary plane is going to be impinging upon that plane at an angle. What we need to do is work out the components of that total stress vector in this XYZ coordinate system. One of the convenient ways of doing that is just to imagine that this stress vector is projected down onto the z-plane. The first of the components that we can work out from this thought is the normal stress acting on the z-plane in the z direction. Now, if we just focus for a moment on the shadow of that total stress vector as it was projected down onto the z-plane, we can use that to work out the component of the total stress vector that is parallel to the y-axis, and similarly the component of the total stress vector on the z-plane that's parallel to the x-axis. So now we have the total stress vector, and we've broken it down into its three components based on the three axes of our Cartesian coordinate system. In other words, we can say that our total stress vector is equal to the sum of its three components. One is perpendicular to the plane and two are along the plane. So sigma t is equal to sigma n, the normal stress, plus sigma y and sigma x. Sigma y and sigma x are acting along the plane. So we say the total stress is equal to one normal stress and two shear stresses. As comforting as the XYZ coordinate system is, what we typically do is sort of upgrade it a little bit with a nomenclature in which we have two subscripts. The first of the subscripts in this case is a z, so sigma zx, sigma zy, sigma zz, and that tells you the plane that we are operating on. These stresses all operate on the z-plane. The second component is telling you what direction the stresses are acting in. So for example, if the stress is acting on the z-plane in the x direction, we call that sigma zx. So here's a little helper. The first subscript tells you which plane we're working on, and the second subscript tells you which direction that we're working. We have a different expression of that equation that we have already looked at. Sigma t is equal to the normal stress acting on the z-plane in the z direction, and two shear stresses, one that's acting on the z-plane in the y direction and one that's acting on the z-plane in the x direction. total stress equals normal stress plus 2 shear stresses. And those are all the stress components acting on the z-plane as a result of the total stress vector sigma t. Now, let's back away from the XYZ nomenclature and do something that at first just seems irritating, but it will pay dividends down the line. So instead of X, we're going to use 1. Instead of Y, we're going to use 2. Instead of Z, we're going to use 3. So we have a 1, 2, 3 Cartesian coordinate system. And so we just make that substitution in all of our sigma subscripts. So sigma 3, 3 is the stress acting on the 3 plane in the 3 coordinate axis direction. So our little block that we started with starts to look like this now with the new nomenclature. The 3 plane, the 2 plane, the 1 plane have the same relationships to those coordinate axes as they did when we were talking about the XYZ plane and the XYZ coordinate system. Each of these 3 planes has 3 vector components. When you add those 3 vector components together, you end up with the total stress vector that's acting on those planes. But this representation doesn't tell me very much. Let's take a look at a slightly more informative way of looking at this. Here we have the vectors of each one of those 3 stress components for a given plane illustrated so you can see where they're going. So if we look at the 3 plane, we've got a normal stress, sigma 3, 3, and we've got 2 shear stresses acting on the plane, sigma 3, 1 and sigma 3, 2. Now if we tally up all the stresses on a given face, we find that we've got 3 stresses, 3 stress components. We've got 3 faces here, so 3 plus 3 plus 3 gives us 9 components. Now, I know that that's not all of the faces of this cube, but it turns out that if you assume that this cube is in static equilibrium, the forces acting on the 3 planes that you can't see are symmetric with the forces that are on the 3 faces that you can see. So we can reconstruct the forces on those unseen faces. In other words, all we really need to work out all of the stresses acting on all of the faces of these cubes are these 9 stresses that you see depicted in this illustration. And so we write them down just sort of in a little list over here. We've got 3 columns and 3 rows, a total of 9 components. And we call this thing the stress matrix. It has some very interesting properties, very particular properties. So let's go ahead and take a look at those. Each column includes the stresses that are parallel to a given coordinate axis. So for example, column 1 includes the stresses parallel to the coordinate axis 1. What else? Well, it turns out that each one of the rows includes stresses acting on a given plane. So all of the stresses acting on this top plane, the 3 plane, are found in this row at the bottom of our matrix, 3, 1, 3, 2, 3, 3. Same for the other 2 faces. What else? If we look at the values that are along the diagonal of this 3 by 3 matrix, we have all of the normal stresses. Sigma 1, 1 is a normal stress acting on the 1 plane, sigma 2, 2, similarly, the normal stress acting on the 2 plane, and so forth. That's interesting. What else? All of the terms that are not along that diagonal are shear stress terms. Okay, so this is a symmetric 3 by 3 matrix. We call it the stress matrix. Displaying these stress components as we have allows us to do useful mathematical things with it that we'll discuss in a future video.